So far, we've taken it for granted that we can represent multiplication by shifting, and we've done it only for small values and generally just to get the correct offsets for arrays of words and half words. Today we're going to have a look in a little bit more detail about how we would do this to represent the multiplication by just a generic value. So let's get started. Well, let's have a look at an example. Assume that the value in T0 is 13, so T0 contains 13. What will the value be after the following sequence of operations? So we have a shift left by 1, shift left by 3, we have a couple of adds there, they're all doing different things. So the easiest way I would say to figure this out is to split it up line by line and figure out what's happening at each stage. So let's do that. So we start off with T0 is equal to 13. And then we do the first shift left instruction, and that's shifting left by 1, which is of course multiplying by 2. We've seen that quite a lot. Hopefully you'll be familiar with this, but shifting left by 1 is the same as multiplication by 2. That's because we change the place values, we move all the place values one to the left, so we get the same thing as multiplying by 2. The next instruction, shift left by 3, well that's the same as multiplying by 2 to the power 3, so that's going to be 8 times 13. Okay, so we shift left by 3 bits. In general, when you're shifting left by n bits, it's the same as multiplying by 2 to the power n. So shifting left by 1 bit is the same as multiplying by 2 to the power 1, which is of course 2. And by 3 is 2 to the power 8, or 3, sorry, which is 8. Then we add these two together, so we get the result of adding 2 times 13 and 8 times 13. And that's of course 10 times 13, because we can rearrange these brackets and sort this out a little bit. And then we add T0 to this value. So adding T0 to this value will give us an odd multiplication of 11 by 13. So if you ever need to make an odd multiplication, you can always just add the original value on to get to an odd number, because the binary values of shifting left by more than 1 will always be multiplications by powers of 2. So if you need to get an odd number, you just add the original value on, and that's all you need to do. Okay, so let's have a look at another example. This is one which is a bit more generic, where we don't know the value, but we want to multiply it by 21. So how would we do this? Well, we assume that x is in A0, and we want to put the result in V0, so let's have a look at how we would do this. The way that we do start generally is to decompose the number to figure out what the powers of 2 that can be added together to get this are. So 21, we know that the highest power of 2 that's less than 21 is 16, because it goes 2, 4, 8, 16. So we'll take the 16, and then if we add 4 to that, that will get us to 20. If we add 8 to it, it would be too much. If we added 2 to it, it wouldn't be enough. So we add 4 to it, which gets us to 20. And then, as with the previous example, we just add a 1 on, and that gets us to 21. So we decompose the number this way so that we can see which powers of 2 we're going to use to get the result. And then we put this into MIPS. So to get the multiplication by 4, we know that that's just going to be shifting left the value in A0 by 2, and we just chuck that in T2 for the moment. Then we want to get the value of 16 times x, which is of course shifting left by 4, because remember it's 2 to the power of 4 that we're multiplying by here, and that will be 16. So we have 16 times x and we have 4 times x, and then if we add into V0 the value of A0 and T2, that will get us 1 times x plus 4 times x, which is of course 5 times x. So we're just splitting this up step by step to make it a little bit more manageable, and then we add into V0 the value of 16 times x, which takes us to the 21 times x. So hopefully this helps you understand this process as we go through it. Generally, the easiest way to do this is to start just by figuring out the powers of 2 that are lower than the number you have, and then putting them together in the right way to get the number you want. So let's have a look at another way to do this. So let's have a look at this example where we have a value of x in A0, and we want to figure out what's in V0 after we've executed this code. So one thing you'll notice here that's a little bit different is that we have a subtraction. So we're doing shift left the value of in A0 by 6, storing that in V0. We're shifting left by the value in A0 by 2. So we're going to get 2 to the power of 6 times x in the first line, which is 64 times x. And then in the next line, we're going to get 2 to the power of 2 times x, which is going to be 4 times x, and then we're going to subtract them from each other to get 60 times x. As you can see here, so first line, 2 to the power 6, gives us 64 times x. Second line, our usual, shift left by 2, that's the same as multiplying by 4. And then we subtract the value in V0, which is the 64 times x. We subtract the value of 4 times x, so we get from 64 times x to 60 times x. Now, why would we care about this to get this value of 60? Well, because this, if we did shifting plus adding, we would need 4 shift instructions, because we need to shift left to get to 32, and then we'd have to add on the value of shifting left to get 16, and then 8, and then 4. So we'd have to do 4 different shift instructions to get all of the necessary multiplications to add together to get the value at the end. However, doing it this way, we only needed 2 shift instructions, which is a lot quicker. Now, this is part of the algorithm, boost algorithm for multiplication, which is quite a cool thing. It allows us to be a bit more efficient in the way that we do multiplication by taking a power just past the value we're looking for and then subtracting the values, a lower value from it to get to the right value. And that can be quite easy if you are quite good if you're close to a power of 2, like here when we were looking for 60, the closest power of 2 was 64. And then the one below that is 32, so you'd have to do quite a lot of work to get from 32 to 60, whereas getting from 64 to 60 is pretty easy. We just do one subtraction of one shift. So that's everything I wanted to cover today. I hope this has been useful. I hope it's illuminated multiplication by shifting a little bit. And as always, if you have any questions about this, please do let me know. Thanks.